So far, we've discussed two types of graphs that summarize the distribution of a quantitative variable, dot plots and histograms. From a dot plot, we also describe the pattern in the data and statements about shape, center, and spread. We have to be more cautious making similar statements using a histogram, kind of like we talked about in the previous page at the very last sentence, because our perception of shape, center, and spread can be affected by how the bins are defined. We investigate this important point in the next example. So the next example will just illustrate exactly what we said, that we can't really come up with center and spread very well with the histogram. But we use the same set of data to construct these three histograms below of student scores. Are you surprised by how different the distributions look in each histogram? Let's see. So in the example below, it looks like these three histograms are totally different looking, especially the very left one, right? In the very left one, there's not a lot of information. It looks like we're talking about grades here. The middle portion, the middle bar, is between 60 and 80. So a lot of students seem to get between 60 and 80%. Looks like it lines up with 9 over here, about nine students, which is the majority. But we don't really know. I mean, 60 to 80 is a very wide range. 60% is not passing, right? But 80 is passing, 70 is passing. So we don't really even know how many students are passing this test or how many even close to it. It's not a great, so kind of with the histogram, you want to make sure there are, I don't know, a reasonable number of bins, I guess, as they called them in the previous page. In the second one, there are how many bins? Let's see, 1, 2, 3, 4, 5, 6. 6 bins compared to 3. There's a lot more information here. We do see that the majority of people are, quite a chunk of the people are between 60 and 80% on their grades, as we saw on the left one. But we see that most of them are in this between 70 and 80. So at least that's kind of nice to know that most of the people in that middle bin actually passed the test or passed the class or whatever the case may be. Now that's the difference between the very leftmost histogram here, this guy, and this guy. The one in the middle has more bins than the one on the left, but you kind of have to look more closely at the one on the right. Think about the one on the right versus the one on the left. They almost look exactly the same. I mean, they're the same number of bins, but the heights are different. So what did they do differently? They just changed the x-axis, sort of. Notice that this x-axis, it's super hard to see. I guess on this page you can kind of scroll down and maybe zoom in on your own. You can see that they go from 45% on the grades to 105. But here in the middle one, they just go from 40% to 100%. So all we did was kind of move the range a little bit to the left. Instead of going from 40 to 100, we moved 40 up to 45 and 100 up to 105. And it just looks totally different. So this one the middle one is almost optimistic. It looks like it's kind of leaning to the right, which are the higher grades, and it makes you happy. But then you look at the right histogram here, and it looks like most of the grades are leaning to the left, which kind of might make the instructor or the teacher sad to see that most students are kind of not doing so good. So it really matters, yeah, which values we pick for our x-axis, kind of, and then also how many bins we choose, obviously. And then as described here, the changes of, the number of bins from the left one to the middle one, and then the range of x values from the middle to the right one, it affects the shape, the center, and the spread of this data. For example, in the histogram on the left, the distribution looks symmetric with a central peak. But in the histogram on the right, the distribution looks slightly skewed to the right. Based on the middle histogram, we might estimate that most students scored between 70 and 80, but the histogram on the right suggests that typical students scored between 65 and 75. So you can kind of imagine if there are researchers or people that are trying to make money off of a product or something, they're going to want to choose a nice visual way to represent their data that'll that'll be advantageous to them. They want to make a lot of money, so I don't know, maybe the people that a medicine helps, they're going to try to make a bar graph or histogram that'll really make it look like it helps a lot of people. They'll change things. The effect of changing bin width and starting point. So those are what we described above. Why does changing the bin size and the starting point of the first bin change the histogram so drastically? When we change the bins, the data gets grouped differently. The different grouping affects the appearance of the histogram. To illustrate this point, we highlighted the 5 students who scored in the 70s in each histogram. In the histogram on the left, the 5 students are grouped in the middle bin with other students who scored between 60 and 80. In the histogram in the middle, these 5 students form a bin of their own, since no other students scored between 70 and 80. In the histogram on the right, these 5 students are in separate bins. So I've kind of shown that here in a nice visual. They said on the very left histogram, they tracked these specific 4 students. There are these little ones in the red dot plot up here, but they all ended up in that middle bar for the left histogram, mixed up with all the people that were scored between 60 and 80. But in the middle histogram, the same 4 students, now they ended up in their own bar, the tallest, the tallest bin, I guess they call it. But it looked like it was a little bit more to the right. It kind of looks like they scored higher than they did if you just look at the histogram on the left. And then when we kind of changed the x values on the x-axis, we kind of pushed them up. Those 4 students that scored around the 70s, percentage-wise, they kind of got split. Some of them were between 65 and 75. So those that scored less than 75%, somewhere between 70 and 75, they were in this leftmost area here. And then those that scored between 75 and 80, were split between the right. So which histogram gives the most helpful summary of the distribution? That's a good question. For this situation, the middle histogram is probably the most useful summary because the intervals correspond to letter grades. So yeah, I'd probably say the left bin isn't super useful the left histogram, because it doesn't have enough bins. Too many students are grouped into one bin. The difference between scoring a 60% to 80%, that's a big difference, but all those people are grouped into one bin. So that one I think is not great. But like I said, I think, at least at our college and a lot of other colleges, students only get A, B, C, D, F grades. They don't get A+, A-, B+, B- type of thing. So that makes sense, like they said, that you would want to group them into letter grades. Between 50 and 60 is a F, and then 60 to 70 is a D, 70 to 80 is a B, so you know how many people are getting an A, B, C, D, F. But the one on the very the very right here, it's kind of a random way to make your x-axis between 45 and 55, 55 and 65. As far as grades go anyway, because grades depend on, what letter grade you get, and that's always between 60 and 70, 70 and 80, etc., etc. So if this were not grades, if it were something else, like calories in a cereal like we talked about before, I don't know if there would really be a better choice between the middle and the right, because maybe the number of calories, I don't know, it doesn't really mean anything as far as like the letter grade type thing goes. But in this case, letter grades are what we care about. How many students got an A, how many students got a B. But the general advice and kind of the lesson for the day in this page is avoid histograms with large bin widths, which means there are not that many bins, that group data into only a few bins. A histogram constructed with large bin widths will show the distribution as a skyscraper. This does not give good information about variability in the distribution. Avoid histograms with small bin widths that group data into lots of bins. So it's tough because not enough bins, they'll all be too big, but too many bins, they'll all be too small and it'll be hard to read. So it's kind of tough, but there should be a middle ground somewhere where there's enough bins, but not too many. A histogram constructed with small bin widths will show the distribution as a pancake. This does not help us see the pattern in the data. So yeah, if you have too many bins, they're just going to be a bunch of them. I don't know. Yeah, like, let's see. Little one here, another one here, another one here. It's going, I don't know. Then it's almost, if there's too many, it just ends up looking kind of flat. There won't be really any tall peaks that you would want to see. So there's probably some middle ground somewhere that would be nice. Not too many, not too few.